Okay, in this video, we're going to be doing Calc BC Problem Set number 30. The problems and a playlist are in the description below. Let's take a look. Number 1, the graph of f prime, the derivative of f is shown above or to the side. It's given that f of 1 is 4. On what intervals is f of x decreasing, concave up, justify? So decreasing, concave up, we're going to need f prime to be negative. We're going to need f prime to be increasing. So let's find the critical points. The first one, we can see them, but we need to find them, right? So the first one is definitely just at 1/2. The second one is at 2, and then the slope of that line is down 3 over 1, so -3, which means that if I go down 1, I'll go over 1/3, so 2 plus 1/3 is 7/3, and then this one is definitely just 7/2. The way I dealt with that, by the way, is the slope, delta y over delta x is -3 over 1. So then delta x over delta y, I do this a lot, but I never really explain it, is -1/3. So now it's like if I move down 1, I have to go over 1/3. It's a little bit more obvious, I guess. I don't know, more obvious to me, but I think about it that way a lot. So we have our critical points. So here's a place where we are negative and increasing, where f prime is negative and increasing. Here's another place where f prime is negative and increasing. So we can say that f of x is decreasing, concave up, on 0 to 1/2 and 3 to 7/2, or 3.5. And our reason is that because f prime is less than 0 and f prime is increasing on those intervals or there. All right, let's look at the next part. Find the absolute maximum of f of x on the interval from 0 to 4. Keep in mind, we know that f of 1 is 4. So what I'm going to do is I'm just going to write down what f of x is. Use an accumulation function. So f of x is 4, the thing we start with, plus the displacement, which will be the integral from 1 to x of f prime of t dt. So I'm using a dummy variable there. I could use f prime of u. You don't want to use f prime of x because x is the upper bound, and that just gets confusing. I'm doing the candidates test because this is a closed interval, so I'm going to say the things that we say, right? F of x is continuous, therefore the absolute maximum is at an endpoint or a critical point by the candidates test. You just get that out of the way. The critical points we know from the previous part are 1/2, 7/3, and 7/2. Now what we do is we make a table that's going to have x and f of x, and then the endpoints and the critical points. So it's going to be 0, 1/2, 7/3, 7/2, and 4. Now we have to find those. What I'm going to do is a lot of geometry. So we got, I should point out, so I highlighted this point. That's definitely the answer, right? If you just think about it, you're decreasing and then you're increasing a whole lot. And then you decrease quite a bit and increase less. That's a relative maximum. It's definitely going to be the absolute maximum, but we have to do the work. So let's do the geometry on this. First triangle we see is 1/2, 1/2, -2. So that's -1/2. The next, I'm going to divide this region up. That's a triangle that's 1/2, 1/2, 2, which is +1/2. I'm going to divide this up. So it's 1/2, that's a trapezoid, 1/2. Then our base is 1/2, our height is 1, and then the sum of the bases is 1 plus 2. So 1/2 of 3 halves. Here, we're going to have a triangle, which is 1/2, a base of 1/3, a height of 1, so that's 1/6. This is also going to be a triangle, and it's 1/2. We have 1/2, and we have 2/3 for the base, and then the height is -2. So overall, -7/6, and then another triangle that is 1/2, 1/2, 2. So 1/2 overall. All right, we're going to use these to find some values. So, for example, at 0, I know that I'm going to get 4 plus 0 because the displacement from 0 to 1 is just -1/2 plus 1/2. It's 0 overall, so that's 4. What I've done, basically, is I looked at this integral and said it was 0. So I'm just going to get whatever I had at 1, which was 4. And then here, we are going to get 4 minus 1/2, which is 7/2. Our reasoning for that is that we did 4 minus the integral from 1/2 to 1 f prime of t dt. For the next part, we're going to have 4, and then we're going to add to that 5/3, which is 17/3. That came from 4 plus 3 halves plus 1/6, and then next up we are going to have at 7 halves, I'm using the 17/3 now and just going from there. So I'm like basically integrating from 7/3 onwards, but I'm like not really explaining that as I go. I get 17/3 and then I'm subtracting 7/6, and the work for that, I mean, if you need to do, it's just arithmetic, but we get 27/6, which is 9 halves. Now I'm going to go from 3 halves, 3.5, sorry, not 3 halves. So I'm going to take this value and I will be adding 1/2 to it, right? Because the integral from 3.5 to 4 is 1/2. So overall, that's 5. Now, in this table contains the biggest possible value and the smallest possible value. We're looking for the absolute maximum, so we can say, therefore, the absolute maximum is 17/3 at x equals 7/3. Let's take a look at the next part. Use Euler's method with 3 steps of equal size to approximate f of 4. This is kind of an interesting question because like we have f prime. Usually we have a function representation of f prime. Here we just have the graph of f prime, but you know we can still find the value of the derivative at each value and work from it. So I kind of like this problem. Also, it should be noted, we already know that f of 4 is actually 5. We calculated it in that table in the previous problem. So let's see what Euler's method does, because that's what you're asked to do. So it doesn't really matter if you do know the value. Let's set up our table, same table every single time, and you should just set it up. We know that we're starting at x equals 1. We're going to go from 1 to 4 and 3 equal steps. So it's 4 minus 1 is 3 divided by 3 is 1. Each step is 1. So we're just going to go to 2 to 3 to 4. That's pretty good because that makes it easier. The initial y value is 4, and we know that the delta x is 1, right? That's what took us from 1 to 2 to 3 to 4. So start with delta x so that you don't forget it. So that's 1. We need the slope at 1, but this is a graph of f prime, right? So the slope at 1 is 2. So 4 plus 2 is 6. We are going to do delta x, which is 1. So, I mean, in this case, if you forget delta x, which you should never do, it's not really going to change your answer, but don't forget to write it. At 2, the slope is 1, because that's a graph of f prime again. 6 plus 1 is 7. And we'll do delta x. We need the slope at 3, which is negative 2. And then 7 minus 2 is 5. So here's the thing. We don't know, I mean, we do in this case, but in general, you don't know that Euler's method has given you the exact answer. So what we do is we say, Euler's method gives f of 4 is approximately 5. It turns out that f of 4 is 5, but there was no way, in most problems, there's no way for you to really know that. It's a coincidence. But I guess, I mean, it's always a possibility. So let's take a look at the next thing. Find f of 1.5 and the second degree Taylor polynomial 2f of x at x equals 1.5. So we do problems like this frequently in the problem sets. And let's see. So f of 1.5 is going to be, what we're starting with is for integral from 1 to 1.5 f prime of t dt. All right, so we got to do some geometry, I guess. So here, I mean, we know, well, do we know? I think we know that at 1.5, we're just going to get 1.5, because if you move over 1/2, you're going to move down 1/2, because the slope there is just negative 1. So here's our little region integral. We have to do, it's a trapezoid, so I'm going to do 1/2. The height is 1/2, and then the sum of the bases is 2 plus 1.5, or 2 plus 3 halves. So that's going to be 1/4, and then 7 halves. So overall 7/8 here. So this means that we're getting 4 plus 7/8. So 32/8 plus 7/8, 39/8. We need f prime of 1.5, but if you just look at the graph, you can see that the slope there, or rather, that's the value, not the slope, right? Because it's the graph of f prime. You gotta watch out for that. Usually I label those. I don't know, I didn't do it here. F prime of 1.5 is definitely 1.5. F double prime is the slope of this graph, and the slope of this graph is negative 1. So we have f prime, f double prime. Now we just use our formula, right? Our Taylor polynomial, f of x is approximately the value of the function, which is 39/8, plus the first derivative, and then x minus 1.5 to the first over 1 factorial, plus the value of the second derivative, which is negative 1, and x minus 1 to the second over 2 factorial. And you just want to always just go through the formula. Even if there's like a 0, I'll often put in the, like, say the fifth derivative was 0, I'll put like 0 x minus 1.5 to the fifth over 5 factorial, so that for the next term I don't mess it up, because I am inclined to mess it up when I don't do that. All right, but that's our answer. I mean, you could simplify that a little bit, but I don't recommend it. I'm just going to leave it as is. Let's take a look at the next problem. Find the second derivative for the path described by parametric equations t cubed minus 3t comma t to the fourth minus 5t plus 1. So this is the path, right? Sometimes you're given the derivatives, the velocity vector. In this case, we actually have the position. So we're going to have to find dx dt, dy dt. Let's do that. Just power rule. So dx dt is going to be 3t squared minus 3. dy dt, again, just power rule. It's going to be 4t cubed minus 5. And from here, we just have to know what to do. So first up, we have to find dy dx. So dy dx, parametrics, is dy dt divided by dx dt. Start with that. And then actually do it, right? So this is going to be the thing we got for dy dt divided by the thing we got for dx dt. If you could simplify this, I would recommend doing that. This does not simplify. But if possible, simplify, because it'll just make life a lot easier. All right, the second derivative, you have to remember this, because it's like, it does make sense, but it's not the, it doesn't jump to the front of your mind as easily as many other things. So it's the derivative with respect to t. So that's, I don't know, that's a writing error. Let me fix that. This should be the derivative with respect to t. Fortunately, I did it right. I mean, first of all, you can't find the derivative of dy dx with respect to x because there's no x's in it. It would just be 0, so that's ridiculous. But watch out. I mean, obviously, people make mistakes. Derivative with respect to t of dy dx, and then we're going to divide by dx dt. All right, so we have to find the derivative of dy dx with respect to t, quotient rule. So it's going to be bottom. Derivative of the top is 12t squared minus top, which is 4t cubed minus 5. Derivative of the bottom is 6t divided by the bottom squared, right? So that's going to be 3t squared minus 3 squared all over dx dt, right? So that's just formula. You can factor some stuff out of the numerator. In particular, you can take out 6t. So if we do that, we're left with 6t cubed minus 6t minus 4t cubed plus 5. Don't forget to distribute the negative. And then all of this is over. We have a 3t squared minus 3 squared, and then divided by 3t squared minus 3. So overall, that's that thing cubed. All over the thing cubed. At this point, there's like not much you can do except for collect like terms. So are there like terms? Yeah, the t cubeds, right? So 6t cubed minus 4t cubed is just 2t cubed. It's the only simplification. Just gonna jump to it. We get this. That's our final answer. There is nothing more to this. That's the end of the problem set. I hope this was helpful, and good luck.